Now the next question we are going to pick up is to express a number as a product of its prime factors. So to begin with, we start with the first, that is 140. So let me just first put up okay. Now 140, if we break it up into factors, it is 2, that's 70. 2 once again, that gives it 35. 5 gives it 7. And so we can write 140 as 2 into 2 into 5 into 7, which can also be expressed where you can leave it as it is, or you may express it this way. That's absolutely fine. Now talking about 156. 156. First we divide by 2. 7s are 14, 2 8s are 16. Then once again by 2 makes it 39. Now dividing by 3 makes it 13, and we know 13 is a prime number, and so 156 can be written as 2 into 2 into 3 into 13, and that once again can we make it 2 square into 3 into 13. Now coming on to the next question, where we have to first find the LCM and HCF, and then we have to verify using the property that the product of two numbers is always equal to the product of LCM and HCF. Now talk about the very first one. 26 can be written as 2 into 13, whereas 91 can be written as 7 into 13. Now over here, first we look out for the common factor in both of them, and we can see that both of them have 13 as a common factor, and so HCF is equal to 13. So what do we do for LCM then? So LCM will be equal to 2 into 7 into 13. We write the HCF. Along with that, we talk about the all the factors which are left out. Now this is equal to 7 2s are 14, and 14 into 13 makes it 182. Now if you talk about HCF into LCM, that makes it 13 into 182, which is equal to 2366. And if we multiply product of the numbers, which is equal to 26 into 91, and if you multiply this, you get the same answer, that is 2366. And therefore the LCM and the product of the LCM and HCF is equal to the product of the two numbers. In a similar way, we shall try to do the second part. Now first we will factorize 510. Now 510 is 51 into 10. 51 is 3 into 17. So 2 into 3 into 5 into 17. Now in a similar way, 92 is equal to, so it is 2 into, let us product it out now, find it out, 248, 224, 212, 26, 23. So it is 2 into 2 into 2 into 2 into 2 into 3. 2 to the 4 to the 8 to the 16 to the 32, 3 to 96, 90. Oh, it's 91. I'm sorry, I read it incorrectly. So that makes it far more easier to understand. 91 is so we divide, okay, 91 divided by, so 7 ones are 7, 7 is 21, so it is 7 into 13, and so the HCF comes out as, just a minute, let me check, 510 is 2, 2 is a 4, 2 5 is 10, 2 5 is 10, 5, 5 is 25, 5 ones are 5, 3, 1 is a 3, 3 7, correct, okay. So over here, the HCF is, because there is nothing common in both, so HCF is 1, and the LCM then is the product of all these numbers. So 5 3s are 15, 2s are 30, into 17 is 510 into 91. So LCM basically is nothing else but 500 into 91, and that is equal to 510 into 91, it's 46410. And again, the product of numbers is also equal to 46410. Hence, both the questions have been verified that the product of LCM and HCF, it is equal to the product of the two numbers. Now, talking about the next question, check whether 6 to the power n can end up with the digit 0 for any natural number n. Before we proceed on with this question, we need to understand one thing. Say for example, we take up any question, any number like say 70. 70 can be written as 7 into 10. Now, because the 10 has been separated, and we know that the the prime factors of 10 are 2 and 5. So, for any number to end in 0, its two prime factors must be 2 and 5, irrespective of the power they get in that. So, for any number to end up in 0, it should have 2 and 5 as its prime numbers. So, over here, if we look at 6 to the power n, now looking at 6 to the power n, we can say 6 to the power n can be written as 2 into 3 raised to the power n. Now, according to the rules of indices, if you have AB raised to the power AB whole raised to the power m, it can be broken up as A to the power m into B to the power m. So, over here we get, using this rule, we get 2 to the power n into 3 to the power n. Here 6 raised to the power n does not have any prime factor as 5, and therefore 6 to the power n cannot end with digit 0. Now, talking about the next one, explain why these numbers which are given in the question are composite numbers. Now, we know that composite numbers, the difference between composite numbers and prime numbers is that prime numbers, they can be factored only as one or the number itself. So, if I have any number which is a product of two other numbers, they may be prime, they may not be prime, but if it is a product of any two other numbers other than 1, then it is a composite number. Over here, if we pick up the first question, the first part of the question, this one, we know that here 7 into 11 into 13 plus 13, we can take out 13 common. So, we are left with inside the bracket 7 into 11 plus 1. This is 13 bracket 77 plus 1, and that makes it 13 into 78. That means the number which is given as 7 into 11 into 13 plus 13 can be written as 13 into 78, which is a product of two numbers, and therefore 7 into 11 into 13 plus 13 is a composite number. On the other hand, in a similar way, you can also talk about the next one. Also, 7 into 6 plus 5 into 4 into 3 into 2 into 1 plus 5. Now we get 5 common from both of them. 7 into 6 into 4 into 3 into 2 plus 1. This is 5 into. Now 7 6 are 42. 42 into 2 is 84. 84 into 12. 7 6 are 42. 2s are 84. 4 12 4s are 48. 4 12 8s are 96. 96 and 4 is 100. So it's 1008 plus 1, and that is 5 into 1009, and therefore this is also a composite number. Now we need to prove that root 3 is an irrational number. So once again we start with the way we did for root 2 is an irrational number. So let root 3 be rational. Therefore root 3 we consider as p upon q, where of course q is not equal to 0. So we have root 3 times q is equal to p, and then we square both sides. So squaring, we get 3q square is equal to p square and therefore p square is a multiple of 3. And therefore p is a multiple of 3. Now, so we assume that let p is equal to 3m. So we substitute in the first equation, and therefore 3q square is equal to 3m the whole square. That is 3q square is equal to 9m square. So you have q square is equal to 3m square, and this again implies q is a multiple of 3. Now because q is a multiple of 3, we get, and therefore p and q have 3 as a common factor, whereas we know that p and q, they should have HCF as 1, and therefore p upon q is not rational, and therefore root 3 is irrational. Now let's try to prove the other part, that is prove that root 2 plus root 3 is an irrational number. So once again we start with let root 2 plus root 3 be a rational number, and therefore root 2 plus root 3 is equal to m, where m belongs to q. Q means the set of rational numbers. Now what do? Squaring both sides. We square both sides. You have root 2 plus root 3 the whole square is equal to m square. Now squaring means a square plus b square plus 2ab. Root 2 into root 3 is root 6 is equal to m square. Now this is 2 plus 3, 5. We take it to the other side. So it becomes m square plus 5. And so finally we have root 6 is equal to m square plus 5 upon 2. Now m square plus 5 upon 2 also belongs to the set of rational numbers. That implies root 6 belongs to the set of rational numbers, but we know root 6 is irrational, which is not true, which is false. And therefore root 2 plus root 3 is irrational. In the next one, it's a very simple one. It can be done straight away. So let 3 plus 2 root 5 is equal to m, where m belongs to the set of rational numbers. This implies 2 root 5 is equal to m minus 3, and that implies root 5 is equal to m minus 3 upon 2. But m minus 3 upon 2 belongs to rational. That implies root 5 is rational, but that is not correct, and therefore 3 plus 2 root 5 is irrational. Hope all of you enjoyed this video on the textual questions